Okay, good afternoon, everyone. It's a pleasure for me to introduce to you today's speaker, Munehito Soda-san. I'm not sure whether I'm pronouncing Munehito appropriately, but he's a very young, bright solar physicist. And he finished his bachelor's from University of Tokyo in 2014, followed by a master's degree on Earth and Planetary Sciences from the same University of Tokyo in 2016. And subsequently, he was a PhD student in the Earth and Planetary Science Department of University of Tokyo. He worked with a very famous person, Professor Yokohama-san, who has done lots of work on solar wind and other related studies on reconnections. And you're probably aware of Yokohama-san's famous work with the Shibata-san and so on. So Yokohama-san was Shibata-san's student as well. So Shoda-san's thesis title was Fast Solar Wind Driven by Parametric Decay, Instability and Alfvén-wave Turbulence. So after finishing the PhD thesis from the University of Tokyo in a couple of years back, he got the prestigious JSPS fellowship, and he's continuing his work, at the Solar Science Observatory, National Astronomical Observatory of Japan, National Institute of Natural Sciences. So he's a very bright young person in our field, and we are looking forward to Shoda-san's lecture today on three-dimensional image simulation of the wave turbulence-driven solar wind models. Shoda-san, all yours.
Okay, so thank you for the introduction. Nice to meet you, everyone. My name is Munehito Shoda from National Astronomical Observatory of Japan. And today I will be talking about my recent works on the direct numerical simulation of the solar wind turbulence and the heating and acceleration of the solar wind. So I'm showing here the actual simulation results performed by us. But before going to the detail of these simulations, I'd like to start from the kind of several fundamental backgrounds. So the solar wind is defined by the continuous supersonic plasma outflow from the sun. And one important problem in solar wind is the heating and acceleration mechanisms. So what I'm showing on the left bottom panel is the radial profile of the temperature of the solar atmosphere. So please take a look at this black solid line. This is a kind of average profile of the solar atmospheric temperature. So the surface temperature of the sun is known to be approximately 6,000 Kelvin. And if you go up, you eventually find drastic temperature jump, which we call the transition region. And from above the transition region, we have a hot expanding atmosphere called solar corona. And from above a certain height, the solar corona is no longer static, but instead the plasma begins to escape from the gravitational potential of the sun and forms a supersonic outflow, which is actually directly observed by Soho Lasco, as shown in the right animation. So the solar wind has a lot of influences to many astrophysical systems, like the space weather forecasting, or it also affects the evolution of the sun itself. So understanding the solar wind is one of the most important tasks in astrophysics. So we have a very famous model of the solar wind, which we call the Parka Model. So what Parka showed in 1958 is that the transonic or the supersonic outflow is naturally formed as a consequence of coronal heating. So if you have a hot expanding corona, then it eventually makes transonic outflow. That is what Parka showed. But the Parka model is unfortunately not perfect. So according to the Parka model, the driving force of the solar wind is a summer pressure force. So it means that if you have hot corona, then the solar wind is fast as well. And vice versa, if you have a low temperature corona, then the solar wind should be slow because the corresponding summer pressure force is weak. But what actual solar wind observation shows is that there is an anti-correlation between the coronal temperature and corresponding solar wind velocity. So what I'm showing here is the relation between the coronal temperature and solar wind velocity. So the horizontal axis is the time, and this blue line shows the solar wind velocity. More exactly speaking, this is an alpha particle outflow velocity, but you can regard it as solar wind velocity. And this black solid line shows the coronal temperature or the plasma freezing temperature. So we can actually estimate the temperature of the source region by calculating the ionization state of the solar wind ions. And by using this method, we can estimate the coronal temperature. And you can clearly find anti-correlation between the solar wind velocity and the freezing temperature or the coronal temperature. So it means that the solar wind from hot corona is slow. The solar wind from cool corona is fast. So it is clearly contradictory to what Parka predicted. So it means that we need a kind of non-thermal acceleration mechanism, an acceleration without the summer gradient force. And because the plasma beta in the corona is low, the magnetic field is likely to play a role in the solar wind acceleration, in addition to the summer gradient acceleration. So the solar wind models can be classified into two types: the wave turbulence-driven model and the reconnection loop opening model. So in wave turbulence-driven model, it is assumed that the energy of the solar wind is supplied by Alfvén waves. So the interaction between the convective motion and the magnetic field generates various types of Mhd waves at the surface. And a part of Mhd waves, in particular Alfvén waves, should propagate upward, and these Alfvén waves are likely to play a role in accelerating the solar wind. So in wave turbulence-driven model, the energy source of the solar wind are the Mhd waves, in particular Alfvén waves. Another promising model is called the Reconnection loop opening model. And in Reconnection loop opening model, the energy source of the solar wind is supplied by the interchange reconnection, the reconnection between the open magnetic field and closed magnetic field. So once the open magnetic field and closed magnetic field reconnect, then the large amount of magnetic energy stored in the coronal loop can propagate into the solar wind, can propagate into the open field region, and it could be responsible for the kind of impulsive acceleration of the solar wind. It is theoretically indicated that the reconnection loop opening model is not likely in the coronal and fast solar wind, but we need to bear in mind that the reconnection loop opening model is highly probable for the acceleration of the slow solar wind. But anyway, in today's talk, I will focus on the wave turbulence-driven model. But again, the actual driving mechanism of the solar wind could be a kind of hybrid acceleration. So both processes should work in the actual solar wind, but I will be focusing on the wave turbulence-driven scenario in the following talk, in the following presentation. This is a schematic picture of the wave turbulence-driven model. So one difficult problem in wave turbulence-driven model is the evolution of turbulence in the solar wind. So again, the energy source of the solar wind in this model is likely to be the surface convective motion, the animation of which is shown here. This is actually taken by Hinode SOT. It's a very clear movie. And by the interaction between this granular motion and magnetic field, a large amount of energy is supplied to Mhd waves, like fast mode waves, slow mode waves, and Alfvén waves. And a fraction of Mhd wave energy can transmit into the corona. And many observations indicate that the energy supplied by Mhd waves is strong enough to power the solar wind. But it is not enough. So because the Reynolds number in the solar wind is very large, it means that a simple viscous heating or resistive heating is not enough to heat up the solar wind. So we have to generate a smaller and smaller scales to have a sufficient amount of viscous and resistive heating. So in other words, we need energy cascading by turbulence in the solar wind. And if you have the fluctuation in magnetic field, it means you have an additional momentum source. So you can accelerate the solar wind by the pressure gradient force and magnetic pressure gradient force, or Maxwell's stress. So anyway, the solar wind can be accelerated by gas pressure and magnetic pressure. So in this model, the most difficult point is to appropriately describe the evolution of turbulence in the solar wind, because turbulence is actually very difficult. So what I'm showing here is the theoretical expectation of the amplitude of turbulence, or amplitude of velocity fluctuation from the solar atmosphere to the solar wind. So this black solid line shows the theoretical radial propagation, radial evolution of the turbulent, the amplitude of turbulence, and each symbol corresponds to the observation. So near the photosphere, we can constrain the amplitude of turbulence by observing the motion of the bright points of the granules. And slightly above the photosphere, in the chromosphere, actually we can observe the fluctuation by observing the oscillation of the spicules. And the Hinode SOT is a powerful tool to diagnose the fluctuation in spicules. And in the corona, we can constrain the amplitude of the turbulence by observing the non-thermal line broadening, which is done by SOHO SUMAR, Hinode ICE, and SOHO UVCS. And if you get much farther from the sun, we actually have the insta measurement of the turbulence in the solar wind by Helios and Ulysses. And recently, the Parka Solar Probe and the Solar Orbiter is working to observationally constrain the amplitude of the turbulence. But anyway, one problem is that we can actually never observe the region where the turbulence is the strongest. So in this region, in this red shaded region, the density is too low to observed by the remote sensing, but it is too close to the sun to observe by the insta measurement. So anyway, by this figure, I don't mean the remote sensing is meaningless or the insta measurement is meaningless. Both are very important, but in order to, bridge the gap between the remote sensing and the insta measurement, we need a numerical simulation to fill in the gap in the red shaded region. So we need everything. The remote sensing is important. The insta measurement is important as well, but also the numerical simulation should help in understanding the solar wind acceleration process, because it is the only tool to diagnose the region in which the turbulence is strongest. So there are three key points in this talk: the Alfvén-wave reflection, Alfvén-wave turbulence, and parametric decay instability. So I will first talk about the first two topics in the following. So the first topic is the Alfvén-wave reflection. So it is theoretically shown that the Alfvén waves are reflected in the presence of density gradient. So this equation shows the reflection rate or reflection cutoff frequency of Alfvén wave. And you can clearly see that the cutoff frequency or reflection frequency is proportional to the density gradient, or more exactly speaking, the scale height of the density. So what I'm showing you in the bottom two animations are the demonstrations of the Alfvén wave reflection. So the red solid line corresponds to the rightward or forward going Alfvén wave, and the blue solid line corresponds to the backward Alfvén wave. And this black dashed line shows the density fluctuation. So by comparing the left and right animations, you can clearly see that if you have large density fluctuation, you eventually have large wave reflection. So the amplitude of the blue line is clearly larger in the right case compared with the left case. So it means that if you have large density variation, if you have large density fluctuation, you eventually have large Alfvén wave reflection. So this is the first topic, Alfvén wave reflection. So the second topic is the Alfvén wave turbulence. So the Alfvén wave turbulence is defined by turbulence driven by the collision of two bidirectional Alfvén waves. If you rewrite the incompressible magnetohydrodynamic equations in terms of accessor variables defined by this, the z plus and z minus, the equations are reduced to a very simple form. So first, let us ignore the right-hand side. Then this equation becomes a simple linear advection equation. So z plus represents the forward propagating Alfvén wave, and z minus corresponds to the backward propagating Alfvén wave. And from this perspective, the right-hand side can be interpreted as an interaction term between the forward propagating wave and backward propagating wave. So if you only have the forward propagating wave, so if the z minus is always 0, then whatever the amplitude of the forward propagating Alfvén wave is, as long as you have the 0 z minus, then the nonlinear interaction term is 0. So in order to trigger the turbulence by Alfvén waves, the amplitude is of course important, but what is essentially important is the presence of the bidirectional Alfvén waves. So this is the second topic. If you have a collision of bidirectional Alfvén waves, then you can trigger the turbulence by Alfvén wave, which is called the Alfvén wave turbulence. So by combining the idea of reflection and Alfvén wave turbulence, we have a kind of standard understanding of the solar wind turbulence, which is called the reflection-driven Alfvén wave turbulence model. So in this model, again, the Alfvén waves can be excited by the interaction between convective motion and magnetic field at the photosphere. And the fraction of the Alfvén waves can propagate into the corona. But because the corona is stratified, we have a gradient in the density. So we have non-zero gradient inside the corona and solar wind. So you have non-zero reflection frequency or reflection rate. So it means that as a natural consequence of Alfvén wave propagation in the solar wind, you eventually have the collision between the bidirectional Alfvén waves, which should trigger turbulence and energy cascading and plasma heating. So this is a kind of standard understanding of the turbulence in the solar wind. But one critical problem in this model is that if you do a direct numerical simulation based on this model, the turbulent heating rate is found to be 10 or 29 times smaller than the required heating rate. So this model, by this model, we cannot reproduce the required heating rate. And because the turbulence is driven by the reflection, it means the reflection is too weak in this model. So although this is a kind of standard model, we have a critical problem that the turbulent heating is too small. And I will move on to the third topic, the parametric decay instability. So we had a problem that the reflection is too small, or equivalently, the turbulence is too weak. And can we solve that problem by compressibility? And the answer is yes. Actually, if we take into account the compressibility of plasma, then it introduces an additional process, which is called the parametric decay instability. So the parametric decay instability is an instability of an Alfvén-wave. And in this parametric decay instability, the initial Alfvén-waves resonantly collapses into forward slow mode wave, forward or acoustic wave, and backward Alfvén-wave. And it generates very large density fluctuation and resultant wave reflection. So what I'm showing in the right bottom animation is a numerical demonstration of a parametric decay instability. So initially, we had the rightward going Alfvén-wave, which is shown by this red solid line. But as the instability develops, we have an exponential growth in the density fluctuation. And finally, we have a large amount of reflected back Alfvén-wave. So this is a 1D demonstration, but if you test this parametric decay instability in the three-dimensional geometry, the system gets much more complicated. So if you have the three-dimensional effect in the saturation phase of the Alfvén-wave, we have turbulent energy cascading and fine-scale structuring. But the basic is not changed. We have large density fluctuation, and as a result, we have very significant amount of wave reflection. So the parametric decay instability is actually a key process to solve the problem. So the motivation of my work is to update the standard model of the solar wind turbulence, including taking into account the plasma compressibility. So to repeat, we had a standard model, so-called the reflection-driven turbulence model. But in this model, we had a critical problem that the heating rate is too small. So we aim to update this model by taking into account the compressibility. And it is expected that if we take into account the compressibility, the density fluctuation should emerge inside the solar wind. And as a result, by this density fluctuation, we have much larger amount of wave reflection, which promotes the turbulent energy cascading in the solar wind. And as a result, it is expected that the heating rate gets much larger to be sufficient to reproduce the realistic fast solar wind. Okay. So the overview of the numerical simulation is shown here. So we take spherical coordinate system from the coronal base to 20 solar radii. So we give up solving the photosphere and the chromosphere because including them inside the computational domain is very computationally expensive. So the lower boundary is taken to be the coronal base just above the transition region, but instead we are more focusing on the evolution of turbulence from the coronal base to the distant solar wind. The basic question is actually very simple. We solve the ideal magnetohydrodynamic equation plus gravity plus thermal conduction and radiative cooling. And at the lower boundary, we impose a fluctuation that to trigger the Alfvén-wave inside the solar wind. And the amplitude of this Alfvén-wave is set to 30 kilometers per second, which is not bad in terms of observation. And the period of the Alfvén-wave is taken to be 100 to 1000 seconds. This is actually corresponding to the time scale of the granulation. So it is also not bad value. And the horizontal axis is taken to be 220 megameter, which is corresponding to the size of the supergranulation. So anyway, although we don't solve the Alfvén-wave propagation from the surface to the coronal base, we can more or less observationally constrain the physical parameters of Alfvén-waves inside the coronal base. So I'm really sure that the simulation is realistic. So this is the simulation result. So what I'm showing here is the vertical cut of the simulation domain. And the top panel corresponds to the temperature, and the bottom panel corresponds to the solar wind velocity. And you can see that the maximum temperature of the solar wind exceeds 1 million Kelvin. And the solar wind, which is the solar wind is not accelerated near the sun, but if you get farther and farther, then you can clearly see the solar wind is gradually accelerated to 600 kilometers per second. So it is a typical fast solar wind. So anyway, by direct numerical simulation, we can reproduce the heating and acceleration of the solar wind. But please remind that the previous models did not reproduce the heating rate. But in our compressional Mhd simulation, we have reproduced the realistic fast solar wind, and it means that we had a sufficiently large heating rate. So I will discuss the difference between this. I will discuss the difference from the previous works. So again, what makes a difference is the parametric decay instability. So just let me repeat, the parametric decay instability is an instability of Alfvén-wave, and as a result of this instability, we have a very large density fluctuation, right? So what I'm showing here are the evolution of the density fluctuation in the solar wind. So the density fluctuation is found to be approximately 20% of the background mean density value. So actually, the density fluctuation is not very large. It doesn't exceed the background value. It is only a few tenths% of the background value. But anyway, we have a ubiquitous density fluctuation in the solar wind. And one shown in the left bottom panel is the spatial profile of the density fluctuation and the growth rate of the parametric decay instability. So this black dashed line shows the magnitude of density fluctuation, which is calculated by the simulation. And what is also shown by this black solid line is the growth rate of the parametric decay instability, which is calculated by analytical formulation and simulation result. So it is clear that if you have large growth rate in the parametric decay instability, then you have the large magnitude in the density fluctuation. So the spatial correlation between the growth rate and the magnitude of density fluctuation indicates or shows that the density fluctuation is generated by parametric decay instability. So the PDI does occur in the simulation domain. And as a result of the parametric decay, we have not very large, but non-negligible magnitude of density fluctuation inside the solar wind. And we have also investigated the role of density fluctuation in solar wind. So in order to show the role of density fluctuation, we have calculated the reflection rate of Alfvén-wave, which is given by this equation. And the result is shown in the left panel. And we have shown two lines. The black solid line is the reflection rate with density fluctuation. So the reflection rate that is just directly calculated by this equation. And what is also shown by this black dashed line is the reflection rate without density fluctuation. So in calculating this black dashed line, we have first smoothed out the density fluctuation in the solar wind and then calculate the reflection rate. So you can clearly see that the reflection rate is significantly small. Gets significantly smaller if you smooth out, if you exclude the density fluctuation. So in other words, in the simulation domain, the Alfvén waves are reflected by density fluctuation, not the stratification of the mean field. So the reason why the density fluctuation enhances the wave reflection is demonstrated by this animation, which I showed in the introduction part. So again, by the collision of the Alfvén wave and the density fluctuation, a significant amount of the forward-going or outward-going Alfvén waves are reflected back. And actually, the density fluctuation is the most important driver of the Alfvén wave reflection. So, and because the turbulence is driven by the reflection and the collision of two bidirectional waves, it means that the density fluctuation is a driver of turbulence, which is the effect of which is ignored in the literature. So I would also like to discuss about the scale difference between the outward going and inward Alfvén waves. So what I'm showing here are the evolution of outward going Alfvén wave and incoming Alfvén wave. And you can clearly see that the scales are totally different. So the outward going Alfvén wave exhibit a kind of coherent structure. So it doesn't experience a strong distortion by turbulence. So it keeps its coherent structure throughout the simulation domain. But on the other hand, if you look at the inward Alfvén wave, then you eventually find a very fine signatures. So it's really chaotic, and you can clearly see that the inward incoming Alfvén wave experiences a strong turbulent distortion. So the scales, the typical scales of the outward going Alfvén wave, the incoming Alfvén waves are totally different. And this scale difference is more clearly or quantitatively seen if you calculate the power spectrum. So what I'm showing here is the power spectrum of the inward Alfvén wave and outward Alfvén wave with respect to the perpendicular wave number. So we show the power spectrum with respect to the horizontal structuring. We take the perpendicular wave number. So we take the perpendicular cut and calculate the spectrum inside this perpendicular or horizontal plane. And for example, if you see the power spectrum at r equals to 6.5 solar radii, then you find significantly different slopes between the outgoing Alfvén wave and incoming Alfvén wave. So incoming Alfvén wave have flat spectrum, which means that it has large energy in small scales, which is consistent with this animation. But if you go further, then the difference between the outgoing and incoming waves becomes milder. You have you still have a difference between outgoing wave and incoming wave, but the difference gets smaller compared with the closer region. And this spectral difference is actually consistent with the theory of weak Mhd turbulence. What I mean by weak Mhd turbulence is the turbulence that exhibits in which the propagation timescale or linear timescale is smaller than the turbulence timescale. So just weakly nonlinear turbulence. So our simulation result directly shows that at least in the energy containing scale, the turbulence in the solar wind is a weak Mhd turbulence. So the linear time scale is smaller than the nonlinear time scale. So means the Alfvén waves propagate from the base of the corona to the solar wind with small turbulent distortion during the propagation through the solar wind. So finally, I'd like to show the direct comparison to the inst measurement Parka solar probe data. So I'm comparing 6 variables. The first one is field strength. The second one is the angle between magnetic field and the radial direction. The third one is the radial magnetic field strength. The fourth one, proton number density, proton-proton beta, and the radial velocity. And I'm showing the Parka solar probe data during the first encounter. And the solar wind in the first encounter of the PSP is classified into 2 types, the active solar wind and quiet solar wind. In the active solar wind, we have a large fluctuation in the radial magnetic field, and consequently the angle between magnetic field and radial direction. We call this abrupt increase in the radial magnetic field as magnetic switchbacks. So in terms of switchbacks, the active solar wind is characterized by the large filling factor or appearance rate of switchbacks. While in the quiet solar wind, the magnetic field is mostly radial. And you also find switchbacks in the quiet solar wind, but the amplitude and the filling factor of the switchbacks is much smaller than the active solar wind. Our simulation result is very close to the quiet solar wind. So, of course, we have a fluctuation in radial magnetic field, but the fluctuation is not so large. But meanwhile, we have a nearly constant magnetic field strength. We have nearly constant proton number density. So our simulation result is can explain the origin of quiet solar wind. In other words, according to our simulation, the quiet solar wind is a purely wave-driven solar wind. But we have still a significant gap between the active solar wind and the simulation result. So we might miss something that makes this gap. So to remember the introduction, so in the formation of active solar wind, the magnetic reconnection could play a role, or we might miss some essential physics or some numerical techniques are not appropriate. But anyway, we still have a problem in explaining the active solar wind, while the quiet solar wind is nicely explained by our direct numerical simulation. And that's it. This is a summary. So one big problem in the previous model of the solar wind turbulence is that the heating rate is too small. So we cannot basically explain the formation of the solar wind in the previous reduced Mhd model, in which the compressibility is ignored. So that's why we perform the compressional Mhd simulation of the solar wind. And using 3-dimensional compressional Mhd simulation, we have successfully reproduced the fast solar wind. And the large amplitude density fluctuation is responsible for this success. So the Alfvén-wave's reflection is promoted by density fluctuation, and the turbulent heating is promoted as well. And interestingly, we have reproduced PSP observation in the quiet phase. So at least a part of the observed solar wind is purely driven by Alfvén waves and turbulence. And so if you're interested in our work, please refer to these works. And that's it. Thank you very much for listening.
Thank you very much, Shoda-san, for a very nice, compact review almost for the solar wind current status. So this is time for questions and comments. So I would request people to use the raise hand option so that I can sequence the questions. So you can unmute yourself after I pronounce your name, and we can take up the questions. If you have a problem with your microphone, you can also use the chat box. So I will follow the chat box questions, and I will pronounce it for Shoda-san's consideration. So time for questions. So please use your raise hand option. I do have some questions, but I will wait for one or two, and then I will take my questions. Okay, so I see a few hands raised already. So Shatabdo, please unmute yourself and ask your question.
Hello, am I audible?
Yes, you are.
Okay, thank you for this intriguing talk. So my question is, from your the solar wind is getting accelerated till around 6 to 7 solar radii. Now that is somewhat contradictory to our understanding from where the drag forces take over as far as the kinematics of CMEs are concerned. So what we know is the drag forces now start as early as at the end of the inner corona, which is around 3 to 4 solar radii. And according to that, the CMEs are expected to travel with a constant speed profile. But given that the thing that you propose, that the solar wind is still getting accelerated at such larger heights, I would expect that the CMEs will show a constant increasing profile rather than a saturating profile. Well, I mean, frankly, such evidence has been seen observationally, but those are really few cases, and it's kind of out of the blue. So what do you think about that?
Sorry, I don't fully understand your question. So I think you're asking about the acceleration as a function of height.
Yeah,
so,
yeah.
And in our simulation, the acceleration finishes approximately at 20 solar radii. And your question is, according to the CMA observation, the acceleration finishes much closer to the sun?
Yes, that's what I'm asking. Yes,
okay,
that's my point.
If the CME is accelerated by the dragging force by the ambient solar wind, then it means that the solar wind acceleration should finish much closer to the sun. But I think the CME acceleration has additional acceleration mechanism. For example, the CME itself has a large magnitude of magnetic field, and it can be responsible for the acceleration. So it depends on the actual acceleration mechanism CME. So, and in my understanding, the dragging force is not the principal acceleration mechanism.
No, so let me just add a few more things. So the acceleration phase of CME can be divided into two parts. There is an initial impulsive phase and then a gradual propagating phase at the end.
Sure.
So what we understand is the impulsive phase is the evidence of the Lorentz force, which you talked about correctly. Now, my point is, since the gradual phase is the phase which very little or almost no acceleration, we are used to see profiles with almost constant speed throughout, let's say after 5 or 6 solar radii maximum. Or even, let's say, at 3 solar radii, the CME turns up with almost constant speed, which is also fed into this arrival time models and so on. So my concern is, I have also seen observational evidences of CMEs which are coming from quiescent prominences. Those CMEs tend to show this linearly increasing profile. But again, those are not the usual cases. Those are kind of the rare cases. So that's what I was wondering. Yeah.
I'm so sorry, but I have no further opinions about the relation between the coronal mass ejection and solar wind. But at least we have a kind of observation of the solar wind by radio wave, which we call the interplanetary scintillation. And according to the observation, the solar wind is continuously accelerated above the 10 solar radii. So it just depends on the configuration, or it just depends on the parameter setup. But anyway, at least the fast solar wind can be accelerated above the 10 solar radii. But sorry, I don't have any clear opinions about the CME acceleration.
Okay. Thank you. Anyway.
Thank you. Very interesting question.
Yeah, I think, the CME propagation models, they do need to have the background solar wind model also appropriately described, because the interaction of the CME as it propagates through the solar wind, depends on the solar wind model, what you use. So I think that's what, Shatabdo's concern is, how well the CME propagation models are compatible with the realistic solar wind models so far. I think it's a really continuing research. There are people in Belgium group, they do work quite closely about the CME and solar wind interaction. I think Bhargav is also here online today. I saw he also does some simulations which are looking after this. So let me take the next question from Ritesh. Ritesh, please go ahead.
Hi, it was a nice and interesting talk. So my question is regarding the density fluctuations, which you mentioned to be about 20% that could be observed here. So is it similar to what Craig de Forest used from the observations based on polarization brightness measurements? So will you call those the blobby structures observed in corona similar to these fluctuations?
Okay. Yes, the blobs are actually observed in the solar wind, but the density fluctuations shown here is not related to the so-called solar wind blobs like shitty blobs, because the blobs in the solar wind are mostly related to the slow solar wind that is blowing out from the streamer region. But we are more or less focusing on the coronal hole solar wind, and the blobs are not frequently observed in the coronal holes. So this density fluctuation is not the so-called blobs. This is a much smaller scales compared with the blobs.
No, because if I can see your scale ranges for about 400 megameters, and the core 2 blobs which he showed are in the range of 50 to 100 megameters or so. So those means I am saying the blobs, but it includes everything, the density enhanced features that are observed. I am not sure if those are also the coronal hole part, because it's mostly from coronagraph images.
Okay, but anyway, this is a very interesting question. Okay. I believe this is the density fluctuation here is really small scale structure. So
I was just going to add that with your permission, Shoda-san. Yeah, I mean, the density fluctuation, what Shoda-san is referring to is more related to the wave phenomena and the turbulence, associated turbulence. And what you are, Ritesh, you are pointing out, probably there are some more instability effects. It could be parametric instability. It could be, a result of, some other reconnections. We still do not know. But to me, I think the blobs which Craig refers to is more of a other instability product rather than a wave-driven product. So these are much smaller scale density fluctuations. I mean, probably maximum is 0.2, could be even much smaller. Yeah.
Okay. Yes, I agree.
Okay. So Pankaj, please unmute yourself and ask the question.
Hi, can you hear me?
Yes, we can hear you.
Yeah, okay. So very lucid talk, Shoda-san. And this is not my field, so I am going to ask very naive question, maybe very naive it may be. So you showed that the turbulence spectrum is different for the reflected and the, outward going and the reflected wave. Yes. In observation, you observe both at a time. So how do you separate that this should be this one or other way around?
Yes, in the nonlinear regime, we cannot exactly divide the forward going and backward Alfvén-wave, but so we just approximate. We just assumed that the LSS variables defined by the LSS variables actually corresponds to the Alfvén-wave. So what I'm showing here is the LSS variables, not the characteristic of the equation, which is defined in this equation. And in the linear regime, this LSS variable exactly corresponds to the forward and the backward Alfvén-wave. But of course, in the nonlinear regime, it is not always the forward and backward. But anyway, we assume that even in the nonlinear phase, this variable corresponds to the outward and inward Alfvén-waves.
Okay, so the can you go to the second last slide? Before, I mean, it's the penultimate slide. I had a question, but I don't remember exactly. Yeah, yeah.
Oh, sorry, which one?
The second, I mean, it's the second last slide.
Second last.
Second
Okay.
last.
Sure, sure.
The one where you show that's observable and comparison. So you said that, okay, the simulation that you perform, okay, the first very naive question is this, that there is a exact anti-correlation between this third column, which is radial magnetic field, and the angle between B and R. So I don't know how much information they add in either sense. To me, it seems that exact anti-correlation. I mean, so one is up, so the other one is down and lower, and I mean, it's whatever way you want to look at. So the trend is exactly opposite. So you said that your simulations is more or less corresponds to quite solar wind.
Yes.
So so what property that you actually check that and based on which you say that okay, it is quite solar wind rather than just looking at this plot?
So that's a difficult question. So the most important factor of the solar wind is that the total magnetic field is nearly constant. So in the quiet solar wind, you can see that you observe the quiet magnetic field strength. And also in a simulation, we have reproduced kind of quiet, constant magnetic field strength. So this is one evidence. And second one is we have a clear correlation between the radial magnetic field and radial velocity.
Okay.
And the simulation will also reproduce this nice correlation between the radial magnetic field and radial velocity. So by these facts, we have we say the simulation result is consistent with quiet solar wind. It's definitely different from the active solar wind.
Okay, thank you.
Yeah, Pankaj, the other thing is, we were talking about, he did mention about the strong switchbacks, which has been discovered by Parka solar probe. So that's the behavior which you see in the left column, which you are referring to actually. So that's a new discovery of termed as switchbacks.
Yes.
Okay. Thank you.
Okay, so more questions? If not, then I will take the privilege to ask few questions.
Sure.
So in the simulation which you showed, and you mentioned that your lower boundary is already in the corona. So my question is, how sensitive is your result in terms of the parameters? You mentioned Alfvén speed about 30 km/s, and this is supported by, of course, non-thermal with observations from Sumer and ICE and so on. But suppose this is 40 km/s. So how sensitive it is, your results based on that?
I have not performed a parameter survey on the amplitude, so this is just my expectation. I think if you, for example, reduce the amplitude, then you have a similar process inside the simulation domain, but you have a little bit slower and cooler solar wind.
Mm-hmm.
But anyway, even though you change the amplitude, the physical processes are common, but the speed and the mass loss rate temperature should change.
Yeah. Yeah, why I'm asking this question, I mean, we have been involved with these observations. So there is always this question of, the non-thermal width has possibilities of different components. It could be because of turbulence, it could be, because of a wave presence. So how do you disentangle the contributions due to different, different components? So this will be probably an upper limit of that. So it is possible that, and there is only a portion of this goes into the solar wind acceleration, part goes into the heating and things like that. So, so that's why I was asking that question. The other point I have is, of course, now you're doing work with the Steve Kramer also. So just for the benefit of, everybody and me as well, can you just give a idea how different is Steve's model and your model?
Oh, sorry, whose model?
Steve Kramer.
Oh, Steve Kramer. Okay. So the Steve's so Steve had a very, very nice model of the solar wind, and his model is first a time-independent model, and second, his model ignores the parametric decay instability. And also his model does not directly solve the turbulence. So, but instead, his model extends from the solar photosphere to the distant solar wind and includes a lot of physical ingredients. So the difference is that our model is better at solving the turbulence and compressional waves, while Steve's model take into account a lot of important realistic physics that we actually ignore. So that is a difference.
Okay, thank you very much. So if I could continue in the same spirit, how different it is from the Suzuki-san's model, because I understand he takes care of a lot of nonlinear Alfvén-wave, effects. So how different it is, your model and Suzuki?
I think you're talking about Suzuki and Initsuka in 2005.
Right.
So this work is actually a three-dimensional extension of Suzuki and Initsuka, which is conducted by one-dimensional simulation. And one critical problem between his model and our model is that the density fluctuation is totally different. So in that model, the density fluctuation is approximately 20% of the background body, while in their model, the density fluctuation is 100% of the background body. It's totally different. And according to the recent Parka solar probe observation, we don't have observed such a large density fluctuation. So that is a difference. But our model is an extension of Suzuki and Initsuka. So we approach the real solar wind.
Okay, very good. Yeah, I'm not able to keep track with that much. So it's good for me to attend these talks and get updated. Yes, I was just going to ask that, this density fluctuation in terms of the observables, what all things we have in hand. So Parka solar probe density fluctuations you are comparing, I presume, and solar orbiter also, is there anything coming up?
So we have a problem that we cannot very accurately observe the density fluctuation in the solar wind, because the density is measured by observing the distribution function. And in order to accurately observe the distribution function, accurately observing the distribution function is very difficult. So we always have the error bar in the density, approximately 10 or 20% of the error bars. So it's very difficult, even by the Parka solar probe, that we have actually have 10 or 20% of density fluctuation. But anyway, one work shows that we have the 10% or 20% density fluctuation with the solar wave.
Yeah, the sensitivity of the instruments has to be improved. Okay, there are a few more raised hands here. So I will request Shamrat to unmute yourself and ask your question.
Hello, yeah, I'm audible?
Yes, you are audible.
Okay, so nice talk. So I just wanted to ask, have you calculated the current density in your simulation? because if you just calculate current density, then you can like infer the Lorentz force, and you can just infer that how much the Lorentz force is contributing to the acceleration of this solar wind. And also with that, you can like infer this plasma pressure variations, which is correlated with this current density or not.
That's a good question. I'm very sorry that I didn't calculate the electric current density, but I have calculated the magnetic pressure force, and it shows that the solar wind acceleration is mostly by the magnetic field, not the gas pressure. So the gas pressure force is only 20 or 30% of the total magnetic pressure acceleration. So the solar wind is magnetically accelerated. I'm sure about that, but sorry, I don't calculate the electric current directly.
No, because one of your slides, I forgot which slide. So the variation of the magnetic field with R was very small. So that's why I was worried that J is how much the value of J you can get from the, I think, so that is field strength. There is one variation of D versus something that with the R and phi direction. Yeah.
At least we have a very fine scale current sheet. We have ubiquitous current sheet inside the solar wind, but sorry, I don't have the absolute value.
Okay.
But anyway, the current sheet is ubiquitously formed in the solar wind, and mostly the current is field aligned. So we have the radial electric current.
No, because from there you can also calculate this interchange reconnection from this current density calculation. So you can hybrid both this reconnection and wave-driven model in your solar wind.
Very interesting. Yes, that could also happen inside the solar simulation.
Yeah. So nice talk. It's a good talk. Good piece of work.
Thank you.
Okay. So next is Vidya Vinay Karak. Vidya, please go ahead and unmute yourself.
Yeah, it's a very nice talk. Thank you. So I have a just quick question. So I missed that, like, what boundary condition you put at the bottom for the magnetic field?
Oh, magnetic field. I didn't talk about the magnetic field, sorry. So we have imposed the radial magnetic field, so radially expanding magnetic field inside the simulation domain. And the magnetic field at the base is fixed to the initial value.
And it's uniform?
Yes, uniform, definitely. Not expanding. It's a uniform magnetic field inside the simulation domain.
Okay. And did you check like some of this result, like how sensitive are they to the boundary condition? I mean, to the lower boundary condition?
So I didn't investigate I didn't do any parameter survey on the boundary condition, but I think it's not sensitive to the boundary condition. Of course, if you change the amplitude or period or the horizontal scale, it changes the heating rate or the time scale of turbulence. But if you don't have any significant change in these parameters, then I think the physics are nearly the same. But what is actually important is the fluctuating expansion factor. So in this model, we assume that the magnetic field expands radially, but in the actual solar wind, the magnetic field expands super radially, and it is actually very important for the solar wind acceleration. So the boundary condition, I think the boundary condition doesn't significantly matter, but the magnetic field configuration matters. But sorry, I don't have any idea.
Yeah, thank you. Thank you. Thank you.
Okay, thank you very much. So is there any other questions? I don't see any raised hand option anymore. So I think I will give just a quick closing remarks. So as you mentioned, the gap between your active solar wind and your simulation probably lies still how you can incorporate the magnetic reconnection scenario also. Maybe, that's, that's the next future. Yeah. Is there any last minute hand coming up? I thought I see something and is appearing.
Yeah, it's from me, Suvendu.
Oh, Suvendu? Okay, please go ahead.
Yeah, so hi, it's nice talk. So I have just a quick question. So how expensive are these simulations in terms of computing resources?
Okay, super good question. in terms of core hours, it takes 10 million core hours. So if you use the, for example, 10,000 cores for this calculation, it takes 1,000 hours.
Okay, I see.
So it's actually a very massive calculation.
Yeah, it's very expensive. Okay, thank you.
Okay. Ritesh again has his hands raised. Ritesh, go ahead.
Yeah, regarding this speed again. So in this particular plot, the speed are in the range of 500 to 700 kilometer per second. And in the last where you showed the comparison with PSP observation, the range at 35 solar radii comes around below 500 kilometer per second.
Yes.
So
what I'm showing, sorry.
Yeah, so you mentioned that you have acceleration till about 20 solar radii. So does it mean after that you have a decrease in speed or something like that?
Oh, sorry. What I'm showing here is a little bit different simulation. Okay. So what I'm showing in the previous slide is the simulation of the fast solar wind. But because the Parka solar probe actually observed the slow solar wind, we did a different simulation that is focusing on the slow solar wind. So I'm very sorry for this confusing presentation. This is a different simulation result, but similar setting.
Okay. Yeah.
Yeah, is the background field and expansion and all that will be also different, Ritesh. So when you want to generate the fast solar wind, your magnetic topology is also slightly different.
Yeah, as Shatabdo asked regarding acceleration, so this thing clicked me.
That's right. So I mean that latitudinal dependence in terms of the CME propagation is also quite crucial. Whether it is flowing through the fast solar wind or the slow solar wind will also make a big difference there. Yeah.
Yes.
Thank you very much, Shoda-san, for a very nice talk and very nice interactive questionnaire session as well. So as you can imagine, we have lots of interest on your work. And although we do have a Indo-Japan program with Kyoto University, and I could have nicely invited you, but unfortunately, because of the last year's situation, we couldn't do that. But I'm hoping that situation will improve and we'll be able to invite you, and we'll be happy to host you here. That we can do some real good work together, probably in near future. So thank you for staying up late as well, because it must be late evening for you to accommodate our usual seminar time. So from Aries, I would like to thank you again, and let's be in touch. Yeah, thank you very much.
I really enjoyed a lot. Thanks.
Thank you.